Section: Introduction. In this section, we will explain our cross-layer attention (CLA) technique and how it relates to the multi-query and grouped query attention architectures MQA and GQA. Initially, the transformer model used multi-head attention MHA, where each query head focused on the keys and values from a specific key value head. However, this led to storing the KV activations of each key value head separately, resulting in a storage overhead per token. To address this, MQA and later GQA were introduced to reduce the storage overhead by organizing query heads into groups that share a key value head. This reduced the storage overhead to a more manageable level. Building on the success of MQA and GQA, which share key value heads within a layer, we propose sharing key value heads across different layers as well. This new approach, called cross-layer attention (CLA), involves computing key value projections for only a subset of layers. The attention blocks in layers without key value projections reuse the KV activations from previous layers. This selective contribution to the KV cache helps reduce the memory footprint compared to traditional architectures that have a separate key value projection in each layer. CLA can work alongside MQA, GQA, MHA, and offers flexibility in adjusting the number of layers that share the output of each KV projection, known as the sharing factor. Different configurations of CLA, such as CLA2 and CLA3, determine how many layers share each KV projection. By varying the sharing factor, we can explore a range of attention configurations with CLA. Section Summary. In this section, we introduce cross-layer attention (CLA) as a method to reduce the size of the key value (KV) cache by sharing KV activations across layers in transformer architectures. By implementing CLA, we aim to decrease the memory footprint of the KV cache by reducing the number of unique layers storing KV activations, offering a new approach beyond existing methods like multi-query attention (MQA) and grouped query attention (GQA). Our experiments demonstrate that combining CLA with MQA can lead to a significant reduction in KV cache size while maintaining accuracy, especially when used between pairs of consecutive layers. Section: Implications for system design. In this section, we will discuss the implications of cross-layer attention (CLA) on system design. CLA mainly focuses on reducing the memory usage of the KV cache, with minimal impact on other resources during model training and inference. When all other architectural parameters remain constant, we can observe the following effects of CLA. KV cache memory. CLA significantly decreases the memory footprint of the KV cache by a factor equal to the sharing factor, or slightly less if the sharing factor does not evenly divide the number of layers. Training memory footprint. CLA reduces the memory usage of intermediate KV activation tensors generated during training, although these tensors are usually small compared to the model's hidden states and MLP activations in models like GQA and MQA. Model parallelism. CLA works well with standard tensor parallelism methods for distributing model weights across multiple accelerators. In the presence of pipeline parallelism, layers sharing a KV cache need to be in the same pipeline stage, or KV activations must be communicated between pipeline stages. Parameters and flops. CLA decreases the total number of key value projection blocks in the model, leading to a slight reduction in the number of parameters and floating point operations (flops) required during forward and backward passes. Decoding latency. In a full large language model (LLM) serving stack, CLA allows for larger batch sizes and longer KV cache persistence, potentially improving inference latency. Core attention latency. Unlike MQA and GQA, CLA does not directly affect the memory bandwidth used by the attention mechanism in each decoding step, as even shared KV cache layers need to be separately read from main memory in each attention layer. In our pre-training experiments, we train transformer-based language models from scratch at 1 billion and 3 billion parameter scales. We aimed to understand the impact of CLA on language modeling accuracy and compared it with plain GQA or MQA. We also explored how CLA interacts with GQA and MQA, identified optimal CLA configurations within a fixed memory budget, and assessed the consistency of CLA effects across different scales. Our findings show that CLA allows for better accuracy, memory trade-offs compared to using plain GQA or MQA. A sharing factor of 2 was found to be more effective, and combining CLA with MQA helped reduce KV cache storage. Additionally, CLA models benefited from higher learning rates and showed improvements at both 1B and 3B parameter scales. Further details of our experimental setup and results will be presented in the following sections. Section Summary. In this section, we explore the implications of cross-layer attention, CLA, on system design. CLA significantly reduces the memory footprint of the KV cache, has minor effects on other resources, is compatible with standard tensor parallelism, slightly reduces the number of parameters and flops in the model, and can improve inference latency by enabling larger batch sizes and longer KV cache persistence times. Additionally, CLA enables favorable accuracy, memory trade-offs compared to plain GQA or MQA, performs well with a sharing factor of 2, benefits from higher learning rates, and is effective across different parameter scales. Section: Design Space Exploration. In this section, we conducted a design space exploration to analyze the trade-offs between accuracy and memory in models with different configurations, with and without CLA. We trained various models using a conservative learning rate and evaluated their performance based on perplexity on a validation set. Our baseline models showed that as we reduced the memory capacity of the KV cache, the validation perplexity increased. We then focused on MQA models combined with CLA2, varying the head dimension from 512 to 64. These models outperformed baseline models with the same KV cache memory, improving the accuracy, memory trade-off. The MQA CLA2 models with head dimensions of 64, 90, and 128 matched the memory footprint of baseline MQA models with smaller head dimensions while achieving significant perplexity improvements. Next, we explored combining GQA with CLA2, finding that only the GQA2 CLA2 configuration achieved a perplexity better than the corresponding baseline model. We also investigated the impact of using CLA sharing factors greater than 2 by training MQA CLA3 and MQA CLA4 models. These models showed improvements over plain MQA baselines but had slightly worse perplexities compared to MQA CLA2 models at the same memory footprint. Section Summary. In this section, we conducted a design space exploration to analyze the trade-offs between accuracy and memory usage in models with and without CLA. By training various models with different configurations, we found that MQA CLA2 models achieved the best accuracy, memory trade-offs, outperforming other CLA configurations and matching or surpassing baseline models with similar memory capacities. Additionally, exploring alternate CLA configurations like GQA CLA2 and MQA CLA3, CLA4 revealed varying impacts on perplexity, with MQA CLA2 consistently showing superior performance in our experiments. Section: Ablation, MQA plus CLA2 with non-uniform sharing patterns. In this section, we explored different patterns of KV activation sharing in our MQA CLA2 models. We trained various models with unique sharing configurations to see how they perform. For example, we created a model called H128 MQA CLA2 keepends, where the first and last layers have their own KV cache, separate from the other layers. We also tested models like H128 MQA CLA2 dense front and H128 MQA CLA2 dense back, with imbalanced KV cache producing layers at the beginning or end of the model. However, we found that these alternative sharing patterns led to higher perplexities and slightly more KV cache memory usage compared to the uniform sharing pattern. We also investigated how different learning rates affect the performance of our models. By tuning the learning rates for our models, we aim to ensure that CLA still provides benefits compared to baseline models trained at their optimal learning rates. Our experiments showed that CLA can reduce the KV cache footprint of an MQA model with d_text head equals 128 without significantly increasing perplexity, or improve perplexity compared to an MQA model with d_text head equals 64 while maintaining the same KV cache footprint. To determine the optimal learning rates for our models, we gradually increased the learning rate until the validation perplexity no longer improved. We found that the optimal learning rate was 1.5 times 10⁻³ for H128 MQA and 2.25 times 10⁻³ for both H64 MQA and H128 MQA CLA2 models. When comparing the models at their best learning rates, we confirmed that CLA2 incurs only a small perplexity degradation compared to the d_text head equals 128 baseline while using a smaller KV cache footprint, and significantly improves perplexity compared to the d_text head equals 64 baseline with the same KV cache memory. Our evaluation on Wikitext perplexity and downstream benchmarks showed that the tuned CLA2 model performs similarly to the d_text head equals 128 baseline and outperforms the d_text head equals 64 baseline. Across different benchmarks, all three models showed comparable performance, staying within 1 to 5 percentage points of each other. Section Summary. In this section, we experimented with different patterns of KV activation sharing in our MQA CLA2 models, including configurations where KV cache producing layers were concentrated at the beginning or end of the model. However, we found that these alternative sharing patterns resulted in worse perplexities compared to the uniform sharing pattern, while also requiring slightly more KV cache memory. Additionally, we conducted learning rate tuning experiments on 3 models to verify that CLA continues to provide benefits even when compared to baselines trained at their optimal learning rates, showing that the CLA2 model achieved similar or better perplexity results with smaller KV cache footprints compared to the baselines. Section. Experiments at 3B parameter scale. In this section, we conducted experiments at a 3B parameter scale to see how well CLA performs on larger models. We trained various models at this scale, both with and without CLA, starting from scratch with 100B tokens from our slim pajama corpus. We used common architectural hyperparameters for these models. In our initial experiments at the 3B scale, we noticed that a model with d_text head equals 64 for MQA performed better than a model with d_text head equals 128. So, we ran another set of experiments with different head sizes. We compared an MQA CLA2 model with d_text head equals 64 to a plain MQA model with d_text head equals 64, and to a plain MQA model with d_text head equals 32. These models were trained on a different cluster and with different software due to logistical reasons. We used a learning rate of LR equals 10⁻³ for all models in this set of experiments. The results showed that the MQA CLA2 model with d_text head equals 64 had slightly better perplexity compared to the d_text head equals 64 baseline model, with a smaller KV cache footprint. It also outperformed the d_text head equals 32 baseline model in terms of perplexity. We also evaluated these models on downstream benchmarks. Overall, we found that the MQA CLA2 model consistently achieved the lowest validation perplexity for a given KV cache memory budget and model size. Using CLA2 with sharing factors greater than 2 showed slightly worse accuracy, memory trade-offs. Applying CLA2 to MQA models with head sizes of 64 and 128 resulted in a 2x reduction in KV cache while maintaining perplexity or even improving it in some cases. This approach can significantly reduce memory overhead with minimal risk. For future work, we suggest evaluating the efficiency of models using CLA for longer sequences and larger batch sizes. Models with long-term memory or those requiring attention over extensive contexts may benefit the most from this approach. Our work focuses on reducing the size of the inference KV cache between passes, while other studies have targeted different aspects of memory efficiency in attention mechanisms. Section Summary. In this section, we conducted experiments at a 3B parameter scale to assess the performance of CLA in larger models. We trained models from scratch on a slim pajama corpus, comparing different head dimensions and finding that the MQA CLA2 model with D_head equals 64 achieved the lowest validation perplexity with a reduced KV cache footprint, suggesting a memory-efficient alternative for practitioners working with MQA architectures. Future work includes evaluating the efficiency of CLA in serving longer sequences and larger batches, especially in models requiring attention over extended contexts. Section: Decreasing KV cache size post-training. In this section, we have explored various techniques to reduce the size of the KV cache in pre-trained models. Many studies have focused on compressing the KV cache through methods like pruning, quantization, and sparsity. For instance, KV-quant and coupled quantization apply specific transformations to keys and values to compress the KV cache to just 1 or 2 bits. Other approaches, such as H2O scissorhands and FastGen, store only a subset of the KV cache during generation by keeping tokens that are close to the generating token or deemed important based on different criteria. Moreover, we have looked into architectural changes that aim to decrease the KV cache size. These changes can be categorized into 3 groups: reducing the number of tokens attended to, replacing softmax attention with operations requiring less memory, and decreasing the unique KV values compared to each query, which is the focus of our work. Furthermore, we have discussed methods that decrease the effective sequence length of models, such as Transformer XL and Sparse Attention, which perform attention in smaller local windows instead of the entire sequence. This approach, known as sliding window attention, has been further developed in models like GPT-3 and InfiniAttention, which compress prior tokens using linear attention mechanisms. Additionally, we have explored alternatives to softmax attention, such as SSMs or linear attention computations, which replace the attention component with alternatives having constant space complexity during token generation. These replacements not only reduce storage but also improve the time complexity of generation. Various methods differ in how they parameterize their state, with recent works focusing on data-dependent mechanisms like GLA-Mamba and RWKV-V6. Lastly, we have discussed methods that use softmax attention but aim to use a single KV pair for multiple queries. Approaches like GQA and MQA group keys and values across heads, while DeepSeek V2 proposes multi-latent attention, which projects keys and values to a lower rank. Another method, You Only Cache Once, divides the model into 2 parts, with the first half performing local attention and generating keys and values used for global attention in the second half.